We're going to walk through 3 examples where we are going to solve a second-order homogeneous Cauchy-Euler equation. Over here on the right, I put the form for a Cauchy-Euler equation of this type, along with the characteristic equation. Let's look at our first example. It is x squared y double prime plus 5xy prime plus 3y is equal to 0. Notice that there is an x squared that multiplies y double prime and an x that multiplies y prime. That's how you know that it's a Cauchy-Euler equation. The solution for this type of equation is y is equal to x to the m. That's where you start. Now what we're going to do is find y prime and y double prime and then substitute them back into our equation. Y prime is m times x to the m minus 1. M is a constant. And then y double prime is m times m minus 1 times x to the m minus 2. Now our equation becomes x squared times y double prime, which is m times m minus 1, x to the m minus 2, plus 5x times y prime, which is m times x to the m minus 1, and then we add on 3 times y, which is x to the m, and set that equal to 0. Let's combine our x's in each term, and we get m times m minus 1, x to the m. The 2 and the minus 2 cancel out. And then we have 5m x to the m. The x to the 1 and x to the minus 1 cancel out. And then we have 3x to the m. Let's now factor out x to the m. So we're left with m times m minus 1 plus 5m plus 3. That all multiplies x to the m, and that's equal to 0. We're going to set this left side of the equation equal to 0 because we don't want x to be 0 because that would just be a trivial solution. This gives us multiplying through m squared minus m plus 5m plus 3 is equal to 0. So we have m squared plus 4m plus 3 is equal to 0. That is our characteristic equation, and we're going to solve that by factoring. We can factor this as m plus 1 and m plus 3. This gives us m is equal to negative 1 and m is equal to minus 3. We're going to call the minus 1 m1, and we'll call the minus 3 m2. The general solution for this equation, because we have 2 distinct real roots, is y is equal to c1x to the m1 plus c2x to the m2. We can now write down our solution. It's y is equal to c1x to the m1, which is minus 1, plus c2x to the m2, which is minus 3. And there's our solution. Let's now look at our second example. It's x squared y double prime plus 5xy prime plus 4y is equal to 0. We start out the same way. We're going to assume that our solution y takes the form x to the m. We'll compute our derivatives, mx to the m minus 1, and then our second derivative, m times m minus 1 times x to the m minus 2. We substitute that into our equation, and we get x squared times m minus 1, x to the m minus 2, plus 5x times y prime, which is mx to the m minus 1, plus 4 times y, which is x to the m, and that becomes 0. Let's combine the x's, and we get m times m minus 1, x to the m, plus 5 times m, x to the m, plus 4x to the m is equal to 0. We'll factor out an x to the m. And we get that. We'll then set this left-hand side equal to 0. So we have m squared minus m plus 5m plus 4 is equal to 0. And we have m squared plus 4m plus 4 is equal to 0. We can factor this. We have an m plus 2 and then another m plus 2 is equal to 0. So we're going to get a repeated root. M is equal to minus 2 and minus 2. When we have a repeated root, the solution takes the form y is equal to c1 plus c2 natural log x times x to the m. So our solution is y is equal to c1 plus c2 natural log x times x to the minus 2. And there's our solution. If you want, let's go back up here to the top. You can just memorize this characteristic equation, and then you wouldn't have to go through the derivation of taking the derivatives and substituting everything in. I wanted to substitute everything in this video because I think when you take differential equations, there are so many formulas to memorize that you might forget that formula. And it's really important to know how to actually come up with that equation. Let's look at our last example. In example 3, we have the Cauchy-Euler equation x squared y double prime minus 3xy prime plus 13y is equal to 0. In example 1, we had 2 real distinct roots. In example 2, we had 1 repeated root. And in this example, we're going to get complex roots. Since I've already gone through the derivation twice, for this one, let's use the formula for the characteristic equation. That formula is a m squared plus b minus a times m plus c is equal to 0. From our equation, we can see that a is the constant that multiplies the x squared, and that's equal to 1. B is the constant that multiplies x, and that's minus 3. And then c multiplies y, and that is 13. From this, we can calculate b minus a, and that's going to be minus 3 minus 1, which is minus 4. Let's now substitute these values into our equation. am squared is now just m squared. B minus a is negative 4, so we have a minus 4m. And then c is 13, so we add 13, and we get 0. That is our characteristic equation. Now we have to solve that. To factor this, we're going to have to use the quadratic formula. So we get m is equal to negative b, so that's minus a negative 4, plus or minus the square root of b squared, so that's minus 4 squared, minus 4 times a, which is 1, times c, which is 13. And we're going to divide all of this by 2 times a, which is 1. Let's see what we get. This is 4 plus or minus the square root of 16 minus 4 times 13, that is 52. And we divide all of this by 2. So this is 4 plus or minus the square root. 16 minus 52 is minus 36. That gets divided by 2. So this is 4 plus or minus 6i divided by 2, which gives us 2 plus or minus 3i. When we have a complex root, m is equal to alpha plus or minus I times beta. So over here on the right, alpha is equal to 2 and beta is equal to 3. The general solution then looks like this. It's y is equal to x to the alpha times c1 cosine beta natural log x. Notice that there's a natural log x there instead of just an x. And then we add c2 times sine beta natural log x. Our solution then looks like this. Y is equal to x to the alpha. Alpha is 2. And then we have c1 cosine beta, which is 3. So we have 3 natural log x plus c2 sine of 3 natural log x. And there's our solution. And that's it. You now know how to solve second-order Cauchy-Euler equations and how to write the general solution in all 3 cases. You should now be ready to work through some practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.